Fuel cells showed how chemistry can turn fuels into electricity without combustion, but the most abundant energy source doesn't come from fuels at all. It comes from the sun. Every second, vast amounts of solar energy strike the Earth, and solar chemistry explains how that light can be captured, converted, and stored using carefully designed chemical systems. This is the Learning Studio, where chemistry is explained as the bridge between natural energy and usable power. And after understanding how hydrogen and fuel cells convert chemical fuels into electricity, the next logical step is to explore how chemistry can harvest energy directly from sunlight itself. Most people think solar energy is only about solar panels, but in reality, it is about how light interacts with matter at the atomic level. For example, when sunlight hits a solar cell and electricity flows, nothing is burning and nothing is spinning. Instead, photons transfer energy to electrons inside a material, freeing them to move and generate electric current. That interaction between light and electrons is pure chemistry and physics working together. At the molecular and atomic level, solar chemistry is based on electronic excitation. When photons strike certain materials, they raise electrons to higher energy states. If these excited electrons are guided through a circuit before they lose energy, sunlight is converted directly into electricity. The efficiency of this process depends on band structure, electron mobility, and how well the material separates positive and negative charges after light absorption. The scientific foundation of solar energy was shaped by Alexander Edmund Becquerel, who first observed that light could generate electricity in certain materials. Later, advances in semiconductor chemistry transformed this effect into practical solar cells, allowing controlled manipulation of electron behavior inside solid materials. Solar chemistry goes beyond electricity generation. It also aims to store sunlight in chemical form. Artificial photosynthesis seeks to mimic plants by using sunlight to drive chemical reactions that produce fuels such as hydrogen. This approach converts solar energy into chemical bonds, making energy storable and transportable, a critical challenge in renewable systems. The chemistry of solar materials determines everything from efficiency to durability. Silicon-based solar cells dominate today because their electronic structure matches the sun's spectrum well, but new materials such as perovskites are being developed to improve efficiency and reduce cost. These advances are chemical at their core, relying on precise control of composition, defects, and interfaces. Solar chemistry also reveals the limits of energy conversion. Light absorption, heat loss, and recombination of charges all reduce efficiency. Improving solar technology means solving chemical problems, stabilizing excited states, designing better catalysts, and controlling molecular and solid-state reactions triggered by light. Once solar chemistry is understood, its importance becomes clear. It offers a path to energy that is clean, abundant, and fundamentally sustainable. The challenge is no longer whether sunlight can power civilization, but how effectively chemistry can convert and store that energy at scale. And once we understand how sunlight can be turned into electricity and fuels, the next question naturally follows. If chemistry can help solve the energy problem, then how can it redesign itself to reduce waste, pollution, and environmental damage at every step? That question takes us directly into the next episode, where we explore green chemistry and how chemical processes are made sustainable from the start.